There's a few different types of near-Earth objects that I'd like to tell you about. The first is an Amor-type asteroid. An Amor-type asteroid, it's very simple. Here's some technical definitions, but the way you can think of it is that an Amor asteroid's orbit is always exterior to the Earth's orbit. So here I show you one of the orbits here. The Earth's orbit is right here, the third planet out. And so you can see that this Amor asteroid is always outside of the Earth from the Sun. There's an Apollo-type asteroid. And the way that you can think of this one is that it can cross the Earth's orbit. See here it's crossing the Earth's orbit there, and it's crossing the Earth's orbit there. But it spends most of its time outside of the Earth's orbit. And finally, the third type is an Aten-type asteroid. Again, it crosses Earth's orbit, but now you can see that it spends most of its time inside the Earth's orbit. Okay, so there's slightly different definitions for these three different types of near-Earth objects. There's also a fourth type, which doesn't have a nice name. It's just called an IEO, which stands for interior to Earth's orbit. And you can see that the definition is very clear. It's an orbit that is always interior to the Earth's orbit. Very simple. Now, another term I'd like to introduce very quickly is something called the MOID. It stands for Minimum Orbital Intersection Distance. It's the minimum distance between two orbits. It's not the same as the minimum distance between two planets. Because the two planets, when the orbits can come very close, does not mean that the planets are at that point. Maybe the planets are at different points in their orbit, so they never actually get as close as the minimum distance between the orbits. And I will illustrate this for you, I think, very shortly. And but before I'm gonna illustrate that for you and then come back to it. So this is an orbit here that you can see. And you can see the Earth's orbit here. And it looks, you can see that this orbit has got a perihelion distance of 1 astronomical unit, and it looks like it meets the Earth's orbit right there. The the object crosses its node, remember the node, at the Earth's point, at the Earth, when the Earth is right there. And so the MOID between these two orbits is 0. The orbits can intersect. Does not mean that the objects do, but the orbits intersect. But now I've taken that exact same orbit. It's exactly the same orbit. But instead of having the perihelion point lie in the plane of the solar system at the Earth's orbit, I have moved the perihelion point north of the solar system. But that's the only thing I've changed about the orbit. The shape of the orbit is otherwise identical. It's exactly the same orbit. I've just rotated the orbit around. And I've moved the perihelion point up to there. And now when I do that, you can see that the orbit has different nodes where it crosses the plane of the Earth's orbit, but where it crosses the plane, it no longer can come close to the Earth. Now the MOID is much larger than 5/100th of an astronomical unit. So that just because an object has a perihelion of 1 astronomical unit does not mean that it will hit the Earth or that it will come close to the Earth. It can be on an orbit like this that will keep it far from the Earth at all times. So now let me go back just a couple slides. And this is the definition of the type of near-Earth object known as a potentially hazardous object. A potentially hazardous object is the subset of near-Earth objects that can approach the Earth's orbit to within 0.05 astronomical units. 0.05 astronomical units is about 8 million kilometers. So any object, any asteroid that can approach the Earth's orbit to within 8 million kilometers is considered potentially hazardous. Because even though it's not going to hit the Earth tomorrow, even though it might not hit 50 years from now, it may hit in 100 years, or it may hit in 500 years. Because orbits in the solar system change very slowly with time. So finally, I told you what NEOs are. Now let me describe what is the impact threat. First of all, impacts do happen. 30 years ago, 40 years ago, this was not known. It's incredible to think that in my lifetime, not your lifetime, but in my lifetime, we've gone from not knowing that impacts happen all the time to being confident that not only do they happen, but they have had major effects on the planet Earth and on life on Earth. Okay? Just a couple examples. Well, before I say that, let me just say that there are no known impact structures in Ecuador. Okay? So maybe that means Ecuador's got some sort of protective dome around it that's bouncing asteroids off, but no, of course not. It's because you have a mountainous country, a lot of geological activity, a lot of erosion that wipes out any evidence of asteroid impacts in your country. On the other hand, where I come from, Canada, it looks like asteroids love to hit Canada, but that's only because Canada is geologically very stable, and it has large areas of land that are very flat and have not changed in a billion years. So anything that hit over the past billion years is still visible there. One of the more interesting impacts that has happened is this one here in the state of Arizona, where I used to work. It's known as very imaginatively meteor crater. And this is about 1 kilometer in diameter. It happened just 50,000 years ago, and it was due to the impact of an asteroid just 50 meters in diameter. So an asteroid, not much bigger than this room, struck the Earth at, maybe twice the size of this room, struck the Earth at 30 kilometers per second and gouged out a hole in the Earth 1 kilometer in diameter. Okay? And to give you an idea of scale, these are the pyramids in Egypt to scale inside the crater. Okay? And this is the Sphinx. Okay? So these pyramids are gigantic, they're huge, right? And they easily fit deep inside the crater that was formed just by the impact of a 50-meter diameter asteroid. Maybe most interesting is this impact location right here, which is on the coast of the Yucatan Peninsula in Mexico. About 65 million years ago, an asteroid 10 kilometers in diameter, struck the Earth at 30 kilometers per second. And when that happened, the surface of the Earth, this is a simulation of what happened to the surface of the Earth at that time. What happens is the impact first creates a giant crater. The Earth then rebounds to create this peak here. The peak then collapses and forms an internal crater. Now, the interesting thing about this is that this peak that got created is 4 times as high as Cotopaxi, right? And it was formed in 5 minutes. And so you have a mountain 4 times as high as Cotopaxi formed in 5 minutes. And then it collapses back down in 5 minutes. This whole event took about 10 minutes to form, and you had mountains 4 times higher than Cotopaxi. And this whole crater here is about 160 kilometers in diameter. Okay? 65 million years ago, many of you were probably dinosaur fans when you were younger, and 65 million years corresponds to when the dinosaurs went extinct. It was this impact off the coast of the Yucatan Peninsula that wiped out the dinosaurs and that allowed us to take over. So what is the risk of dying now? What is the risk of you all dying due to an asteroid impact? This is the fatalities, deaths per year, per event, due to an asteroid impact ranging from about 10 meters to 10 kilometers in diameter. And you can see that there's this major change here at about 1 kilometer or 2 kilometers in diameter. This is, I don't want to go into the details, but what happens is that at about that size, somewhere between 1 and 2 kilometers, an asteroid impact has global effects. It doesn't just affect Ecuador or South America, it affects everywhere in the world. And a single asteroid impact, 1 or 2 kilometers in diameter, would immediately kill 1 or 2 billion people. And then it would make the Earth a very bad place to live for the next year or two for everybody to survive. Below this global limit, the effects decrease dramatically. But still, you can see that 100 meter diameter impactor, 100 meter diameter asteroid, about the size of a football field, could kill 10,000 people on average. 100,000 people on average. 100,000 people due to a 100 meter diameter impact. Now that last figure I showed you was for the situation about 20 or 30 years ago, before we had started doing our surveys for these asteroids to try and identify them. Nowadays, sorry, this one is, this is the one showing about 30 years ago what would happen if an asteroid impact was to take place, because at that time we did not know where all the asteroids were. But now, over the past 30 years, we've identified about 90% of all the asteroids that are larger than 1 kilometer in diameter. In other words, we've identified 90% of all the asteroids that might cause a global effects. And so that we've reduced the risk then of an unknown impact by 90%. So this, the fatalities per year now look something like this. This is on average, over the course over many, many years, we would expect to have something like 20 people die every year due to asteroids that were 2 kilometers in diameter. But you can see that every year, asteroids just 50 meters in diameter kill 10 people or so. Now, of course, I know you're wondering, why don't we hear about these things more often then? How can it kill 10 people per year, 5 people per year? But this is averaged over 1,000 years or 1,000,000 years, okay? So, yes, maybe in the last 100 years, nobody was killed by an asteroid impact. But that's just luck, because in just 100 years ago, in 1908, there was an impact in Siberia that wiped out 1,000 square kilometers of land. And had that impact taken place over a city, it would have killed 1,000,000 people. But of course, most impacts occur over water or over uninhabited land, and so they don't kill anybody. So this is all just an average. One way I like to think about it is that in this century, in your lifetime, the odds of a major impact happening, something that would wipe out Ecuador, is about 1 in 1,000. So 1 in 1,000 chance of wiping out Ecuador, or an area the size of Ecuador, this century. Another way to look at it, well, that's another way, I'll move on here. So finally, how do we find near-Earth objects? I hope that I've told you what they are, and I hope I've convinced you that they're dangerous. So how do we go about finding them? Well, there's a few different surveys, sky surveys, that take place around the world, mostly in the United States. And mostly there's just about 2 or 3 that are really finding the vast majority of objects. 95% of near-Earth objects are found by just 3 or 4 telescopes. One of them is this Catalina Sky Survey that takes place in southern Arizona, outside of Tucson. Another one is the Spacewatch Survey that is on another mountain just outside of Tucson, Arizona. And this one here is the one I worked on. It's not as old as your Quito Observatory. It was, this one was built in 1930, so it's 100 years younger than your Quito Observatory telescope. But I spent many nights working that telescope, probably 6 nights a month for 3 years. That's a lot of time to be spending observing. And I also did spend time up there when there was lightning taking place, and even in the dome when a lightning struck it. It was a quite interesting experience. What we do at all these facilities is we take multiple images of the sky to find the asteroids. So we might take an image at midnight, come back half an hour later, take another image of exactly the same section of sky, and come back another half hour later and take yet another image. And then we, in the computer of course, we superimpose those 3 images, and then we rapidly sequence between the images to try and look for any differences. Now, what you're seeing here is a galaxy. This here's a galaxy, actually many of the things you see here are galaxies. Things that look point-like are typically stars. Galaxies and stars are very, very far away. And yeah, they do move across the sky, but so slowly that in a human lifetime, it takes extremely sensitive instruments to measure their movement. But asteroids and comets are in our solar system. And our Earth is moving around the sun. The asteroids and comets are moving around the sun. And so we can see the apparent position of the asteroids and comets changing during the course of just 1 hour using these telescopes. So in the computer, we sequence between those 3 images very quickly, and if you look for things that are moving. And if you look up here, you see 3 dots of light, and if you look down here, you see 3 dots of light. These are 2 asteroids in the same field of view that are moving relative to the background stars. Right? So this is how we find asteroids. And it used to be, up until 25 years ago, that people did this by eye. And and I don't think I would ever want a job like that. So I'm very glad right now that we have computers and CCDs and digital cameras that can do all this stuff for us. So that's how we find them. Now we start getting into some more technical details. How many NEOs are there? And what is their source region? Okay.